144,000 people are aboard the starship Inspiration, fleeing a dying Earth. To achieve interstellar speeds, they rely on a massive Earth-based laser beamer network to push them outward. Shortly after launch, the crew discovers the fatal compromise. Political authorities on Earth lied about the beamer network's capacity. It is drastically underpowered, leaving the ship stranded before it even clears the inner solar system. The mathematics of this betrayal are absolute. Without that external thrust, a journey planned for 4 centuries balloons into a 14,000-year crawl. Every person aboard will die in transit. Survival requires a desperate pivot. The crew calculates an emergency diversion to the Saturn system to harvest raw materials and construct their own replacement beamer, a high-stakes maneuver known as the Titan bargain. This survival plan provides the narrative foundation for the Centauri Covenant saga. Today, we're running this emergency detour through real-world orbital mechanics and NASA planetary data to see if the physics actually hold up. First, let's look at the arrival. Rather than aiming directly at their primary target, the moon Titan, the crew cuts the Inspiration's engines early, brakes during the long transit, and settles into a wide elliptical orbit around Saturn. In orbital mechanics, every maneuver is constrained by delta V, or the required change in velocity. Intercepting a moon while carrying interstellar speed would demand a mathematically fatal amount of propellant. Attempting to orbit Titan directly would simply exhaust the ship's remaining fuel. This wide elliptical insertion strategy mirrors the real-world trajectory used by NASA's historic Cassini mission to enter the Saturn system safely. By avoiding a fuel-heavy capture at Titan, the ship preserves its ability to maneuver. The authors followed verified orbital mechanics to make the trajectory possible. Once parked around Saturn, the crew must build a laser relay from scratch. Their plan relies on a cosmic supply chain strung across 4 specific moons to bootstrap an industrial economy. Titan serves as the primary fuel source. NASA's geological surveys confirm that Titan's dense atmosphere and methane seas provide the nitrogen and hydrocarbons the ship needs for its refineries. For water, they send tugs to Enceladus. Cassini's observations of the moon's plumes confirm that water vapor and volatiles erupt directly into space, providing a highly accessible orbital resource. Rhea provides the necessary shielding. The moon's heavily cratered surface is composed of bulk ice, making it an ideal quarry for the ship's protective mass. Finally, the crew targets Dione for silicate rock. Data from the Saturn system indicates Dione possesses the rocky fraction required for the ship's construction needs. The planetary science here is accurate. The specific geology of these moons aligns exactly with the raw materials required for an industrial foothold. While the materials are available, assembling them is a different matter. The crew sacrifices 2 of the ship's nuclear reactors to bootstrap a cryogenic processing plant and a multi-million-ton phased-array beamer in orbit above Titan. The chemical extraction process is theoretically sound, but the speed and scale of the construction break the laws of current industrial practicity. The Tsiolkovsky rocket equation shows a strict mathematical limit for advanced fusion exhaust velocity. As spacecraft mass increases, the fuel requirements spike on an exponential curve. Hauling that much infrastructure ruins fuel efficiency, and the challenges only grow at the microscopic scale. High-end semiconductor fabrication requires controlled cleanrooms and ultra-pure water, infrastructure that is nearly impossible to build in a few years within Saturn's orbit. The underlying chemistry is real, but the timeline and industrial capacity push the Titan bargain into the realm of speculative fiction. Running the numbers reveals a split verdict. The astrophysics, orbital mechanics, and planetary geology of the detour are 100% real, while the manufacturing timeline stretches the limits of engineering. Anchoring the setting in hard science converts the crew's desperation into a mathematically verified trap. This schematic shows the permanent cost of that trap. To save the mission, the crew was forced to amputate the ship's infrastructural heart, leaving 2 of their reactors and a portion of their own crew behind on Titan forever. Saturn provides the raw chemical building blocks for survival, provided the crew is willing to pay the brutal price of extraction.